Hi, you might be wondering what this is. It is not an oil refinery. This is a desiccant-based air conditioning system. We've already done a couple of videos on a thermoelectrically cooled or Peltier cooled refrigerator and freezer. And in that case, because you can really well insulate the enclosure, you can compensate for the low efficiency of the Peltiers and take advantage of some of the convenience factors. But with an air conditioning system, the problem is it's expensive to produce really good insulation for a large building, and it's very expensive to try to retrograde engineer better insulation to existing structures. So the name of the game with air conditioning systems is efficiency. There is an industry term called COP or COP or coefficient of performance, and that is the amount of heat energy measured in watts pumped per watt of energy expended in the process. And the higher the COP, the more efficient the unit is going to be. This system here is far more efficient than a typical compressor-based phase change air conditioning system. And the working fluid in this case is water. Water is a remarkable fluid in that it consumes or it uses a tremendous amount of energy to change the phase of the water from a liquid to a vapor or from a vapor to a liquid. It takes 5 times as much energy to take 100 degrees centigrade water and convert it into 100 degree centigrade vapor as it takes to take that same quantity of water and bring it all the way up from 0 degrees freezing cold all the way up to 100 degrees centigrade in the first place. And conversely, the same amount of energy is released when that water vapor condenses to a liquid. So to take advantage of that, what we are going to demonstrate here is the power of that phase change in water. And I'm going to set up a little apparatus here to just show you how potentially powerful that kind of application can be. Okay, what we're using throughout the build is some 4-inch ID or 100 millimeter Schedule 40 PVC pipe. We have some piping here. We have a elbow or T-fitting here. And I've welded on the bottom of the T-fitting a small segment to create a reservoir for water here. In the bottom, as well as on the top, I've connected a threaded fitting to this large diameter tubing. And a neat trick for doing that is to take the fitting that you intend to connect to whatever diameter tubing that you're using. You place a piece of sandpaper on it to form a curve, and then just simply by drawing this back and forth about 30 or 40 times, takes less than a minute, you can grind a radius in here so that it will fit on the tubing and provide a nice tight seat. What we did in the spray component here is that I fabricated one of these welded fittings with the curvature placed in it, and then using a solvent cement, I placed a piece of tubing on there, and then when this was dry, put a little bead of epoxy and pushed it onto the hole that I drilled in the side of this. Then I was able to weld an elbow, another piece of PVC pipe here in which I've drilled some holes, a cap in which I drilled a hole to provide a spray nozzle to distribute the water that's going to be pumped up to the top of the evaporator. In the base of this reservoir T-fitting, there is a piece of mesh. This is a nylon mesh that I've placed inside of the tubing. What the purpose of this is to keep these, called bio balls. Anybody familiar with wet-dry filters in fish tanks or aquarium know that they're used to increase the surface area for the interaction of air and water. They're inert, they're made out of either nylon or polyethylene. And if we fill the tube with this, we're going to provide a larger area for the water and the air to interact. So what I'm going to do, now that the mesh is in there, is I'm going to fill this up with a quantity of these bio balls. And you can obtain enough of these to do this entire system. Each of these stacks has these bio balls placed in it to be able to do that entire setup here for about $30. And as I'll get into later, there are other options. That's full enough for now. And then we're going to add the pipe. And then I'm going to keep adding them till we get up near the top. About now. And then the nozzle will go up here on top. And then to prevent any spray getting into the air that's going to be flowing out of here, we'll add a few additional bio balls above the outlet from the spray. Now, what I'm going to do is I'm going to weigh this entire structure here. So we'll get a known weight for the components, and I'm going to bring this over to this scale, and we'll zero this. Okay. Now, as you can see, we have about 4.95 kilograms. I'm going to call this only 4 to be very conservative because we're not going to really involve the fan or the pump in this process. Plastic, PVC, polyethylene, has about 1/4 the thermal inertia of water. It takes about 4 times as much heat to warm a quantity of water as it takes to warm the same mass or weight of plastic. So effectively, we've got about 1 kilogram of water inertia here. And what I'm going to do is I'm going to add 2 liters, 1,000 cc's, to the top of here. Okay. Now, what we're going to do is we're going to hook this up to a temperature meter, and what we have in here is an inline temperature probe to measure the temperature of the water that's circulating in this loop. And then what's going to happen is the temperature of the water will drop as it's being circulated through here, and there's a countercurrent of air going upward. And then what we're going to do is we're going to time how much temperature is actually lost. So we have a given amount of thermal mass, and we have a time, and you'll be able to see on the power supply, we have a number of watts used to accomplish this. And then we'll be able to calculate what the COP, or coefficient of performance, of this evaporative system is. This is a baseline for everything we're going to do from this point on. All right, and then we're going to measure the starting temperature, not the air temperature. So let's turn this on. About 15 watts. Temperature is measuring 20.6 degrees. Let's go. Okay, 14 degrees. We've used 16 watts. We've gotten a temperature differential of 6.6 degrees. So the amount of cooling we got was 3,000 cc's equivalent of water times 6.6 degrees. So effectively, we've gotten about 20,000 calories of heat removed from this water, which is about 80,000 joules. And we used 16 times 300, or about 5,000 joules. So we have a COP with this system, or a coefficient of performance, of about 16 to 1. Now, a typical room air conditioner has a COP that's about 4 or 5 times worse. I'll show you the little one that we have here mounted in the lab. But you'll see that with this system, you can do some pretty impressive cooling. Now, for you skeptics out there, you might say, well, yeah, this is just a swamp cooler. You've converted temperature into a high humidity. With a desiccant-based system, though, you can fix that. You can compensate for that. If what you do is you place a desiccant material in front of the airflow. So effectively, you pull off humidity before you reintroduce it. You can bring the humidity down to near zero and then bring it back up to ambient without adding any additional humidity and get this high efficiency of cooling. Now, one of the challenges, though, with desiccant-based systems is that the adsorption, that's with a D, meaning surface adsorption process, decreases entropy and it releases heat, so that the air that would come off of here to be brought into the cooling column would be warmed in the process. You can easily deal with that, though. You can take that dry and warmed air and bring it back down to ambient by simply taking a couple of radiators, and one radiator pulling the air through from here and the other one in a closed loop, taking the air temperature, taking the heat out. It only takes a watt or two to move enough air to be able to reduce the temperature here back down to ambient. The other problem you have with a desiccant-based system is obviously at some point the desiccant is going to become saturated. It will no longer be able to pull water off. And dry-based desiccant systems have been around for dehumidification and even refrigeration systems. And in order to use them, what typically is done is they pack a large quantity of this material, because it's not very efficient, into a great big disc, a perforated disc, that slowly rotates in front of some wedge-shaped ducting. And so through one, say 120 degrees of its circumference, the air is pulled through, dehydrated, and sent to an evaporative column. As the disc slowly rotates, that moisturized or saturated desiccant, it then moves in front of a hot air stream, which then draws off or drives off the humidity. And then as it moves to the third section in that rotation, in a sealed system, the heat is then allowed to be released. The desiccant cools back down to ambient as it returns into the airflow. The problem with those systems is to keep them efficient, you want low-speed air velocities. And so with an inefficient absorbing material and with the desire to keep the ducts large, this becomes mechanically very large, very bulky. And it isn't very efficient because solid desiccants aren't that efficient. But there's a better alternative, and that's what we're going to show you today. Okay, so desiccants, dehumidifiers, and even refrigeration systems have used solid desiccants for many years. But very recently, liquid desiccants have come to the fore as being a much more convenient and even more effective way of dehydrating air. This Erlenmeyer contains distilled water. This Erlenmeyer contains liquid desiccant. Now you might think this is some sort of exotic liquid, but it isn't. This is 35% road salt, calcium chloride, and water. That's it. It's almost free. And its ability to desiccate is pretty substantial. If I were to leave these two flasks in here for a week, the level of the water would actually drop due to evaporation, and the level of the desiccant solution would actually rise as it absorbs water from the atmosphere. It would take too long for me to demonstrate that here. So what I'm going to do is I'm going to place these in a warm bath, and you're going to see an interesting phenomena occur over the next couple of minutes. So we're going to attach this large diameter coupler between the two of these. Good enough. And then I have some warm water. I'm going to put this in this basin. So both flasks will be at exactly the same temperature. There we go. Keep an eye on the sides. Now what we're going to do while this is going to demonstrate what's going on here, I'm going to go through the overall flow and principles engineering behind this entire system. And I'll kind of show you where things are going and how we're going to accomplish the air conditioning in a practical manner. All right, so what's occurring here is each one of these three columns are almost identical in that they're filled with bioballs. They have the same flow patterns. Air is pushed in, rises up, water or desiccant pour down, water pours down. So they're countercurrent evaporators, dehumidifiers, and desiccant refurbishers. You'll see that there's a little radiator on top of a burner that provides heat so that the flow that's going to be coming up through here and measured at this probe is going to come to the top of this column and drizzle down through the bioballs as the air that's pumped through the bottom is rising up. What this will do is this will dehydrate the desiccant solution that is being pumped up to the top. When the fluid reaches the bottom here, it will be dry, it will be concentrated, but it will be quite warm. And so then this pump will pump this through to an evaporative cooler on the other side, where a similar radiator like this is immersed in a water bath, and where air being flowed by these fans through these evaporators will cause a lowering of the temperature of the desiccant, which then will exit here and rise to the top of the dehydration column. At this point, the now cool and concentrated desiccant will drip down through here, and then the fans over here will pump air that will then be dehydrated as it rises through the column. It goes past a temperature probe down through this loop here. It's now dry but warmed by this process because, as I said, the desiccation process warms the air. So when we pass it down through here into this box, there's another radiator in here, and this radiator is then hooked up to the second evaporative bath over there in a closed loop. And so by going up and down in a sort of zigzag pattern through this radiator, what comes out here is now dried and cooled. This then will pass through a coupling here into the bottom of the final evaporation column, which is what you saw demonstrated a little bit earlier. And then the air that comes out of the top will be the properly air-conditioned or cooled air. What we're going to do before I actually demonstrate how well this performs is I'm going to turn on the evaporative pre-coolers over there and let them run for about 20 to 25 minutes, because right now the water in there is at room temperature. Once I start the evaporation process, there's a fair amount of water in there. The temperature will drop down to an equilibrium temperature, and that's what is going to be accomplishing the cooling of the desiccant as well as the pre-cooling of the air over here. There is a German company that has begun introducing desiccant-based refrigeration systems, and they've demonstrated a substantial improvement over regular phase change compressor-based systems. They are not incorporating this evaporative cooling stage, and even so, they've gotten a doubling of the efficiency over a regular air conditioner. So this is something that we came up with that turns out it works very well and adds substantially to the efficiency of the system. Basically what's happening here is that in this unit, we just have a fluid loop, and the water is being pumped out of the reservoir and to these small PVC pipes that are running underneath the fans. Each of the pipes has a small hole cut right above where the evaporation is occurring. So they dribble water down over these evaporators, but substantially more water than is evaporated, so the cooling effect on these evaporative wedges here then pours down into the desiccant, into the liquid in the base, and so the whole reservoir drops down in temperature, but obviously that would take a little bit of time. These fans are extremely low speed. The total consumption of power here is about 3 watts for both of the evaporative coolers. These pumps only use about 1.5 watts. In this case, we have a radiator down here because we have to self-contain, or we have to contain the desiccant. In the other unit, we're simply taking that cold reservoir water and using it as a closed loop between the evaporator and between the radiator that's contained inside of the box. And as you can see, right now it's reading at about 15.3 degrees. And we'll give it about 20 minutes and see how much colder we can get this just by using evaporation. And before I leave you, I think we can take a look at what's happened to the desiccant. If we left this here for a couple of hours, we'd actually see a level change. But you'll notice all the humidity that's condensed on the sides of this Erlenmeyer above the water level, but no humidity here. This is actually pulling the humidity in the air here into this container here. That's why this is completely clean or clear, and this one has a fog on the inside. This stuff really works. Okay, we've pretty much reached an equilibrium temperature here. I've left it go for like 1.5 hours and it's just not dropping anymore. It took about a half hour to get here, but I wanted to assure that. So based on the room temperature and the cooling tray water temperature, we've got a pretty good differential here for these pre-coolers. So what we're going to do is I'm going to disconnect this here, and I'm going to move this meter over here to measure the temperature of the heated desiccant in this tubing here, and connect this probe up here to measure the outflow temperature from the dryer stack over here. So put this over here like this. There we go. And then finally, I have a temperature probe located up here to measure the temperature of the final column of air when it comes out. I have a little anemometer that we're going to use to measure the airflow velocity out of here. And I'm going to show you right now that the diameter on the output coupler here, this is a 6-inch scale, so it's about 4.5 inches across here, or about 113 millimeters, which is about 1/100th of a square meter. So we'll be able, with the velocity and the area, to determine the actual quantity of air that's pumped through here, and then we'll measure the temperature differential. We can determine watts of cooling. Now, a couple of additional caveats here. If you look back here, you will see a tube that connects the two reservoirs down here. And the purpose for this tube is that even though the two pumps, which are pumping the fluid, or the desiccant, out of the two reservoirs, are identical and powered at the same voltages, and even though I have these clamps to fine adjust the flow to try to equalize it, if it's not absolutely perfect, over a period of time, what will happen is one reservoir will drop at the expense of the other. If I adjust it pretty closely, all that overflow tube will do is take care of that little minuscule buildup over time to keep the two reservoirs at the same level. Another interesting thing is, if you look at this radiator here has stainless steel tubing in it. Its sister inside the bath in this evaporative tray also uses stainless steel tubing. We need to do that because we're using a corrosive salt mixture in here. And these things can be obtained on eBay or Surplus. We got this from a Surplus Laser, but any kind of industrial equipment that uses DI water for its cooling will have stainless steel tubing, and that's compatible with this mixture. The radiator that I showed you before in here consists of aluminum, simply because we're using distilled water between that evaporative cooler and this one in here, so you can get a little bit less expensive radiator for this function over here. Now, one of the things also is that these baths back here consume a fair amount of water in the evaporative process. But that water does not have to be high quality water. It shouldn't be sewage, but effectively you can use gray water. You could even use seawater for this, as long as periodically you flush this so that the concentrating salt solution in here is flushed out. You don't need to use expensive pure water for this evaporative function, unlike the evaporative cooling stack at the very end over there, which does need to use clean water because it's going to be getting into the air in your room. So you're obviously going to be consuming a little bit of clean water with that. Now, another important feature is that these two stacks are dealing with salt water. And when you're blowing air through them, you want to vaporize that salt water, but you don't want to get the salt into the air. So an interesting thing you can do to test that is you can take a little popsicle stick, spray a little water on it, like that, taste it, pine, and then place it in the outflow from the stacks. And what that effectively will do after a half hour or an hour, if you then take it off and taste it, there should be no salty flavor to that. You've added no salt to the air. Now, if that happens, one of the reasons that might be is that if you don't have enough bioballs or surface area to block any kind of spray from that nozzle at the top, you can get water droplets or desiccant droplets into the air. So by adding additional bioballs above there or adjusting the speed on your fans, you can make sure that the salt doesn't get into the air. Once you've assured yourself of that, there's another neat option, and that is we're using calcium chloride in here, which costs pennies. But if you do elect to go to lithium chloride, which is an even more effective desiccant, it's about 3 times as efficient as this desiccant. It costs a lot more. You may spend $20 or $30 to fill up a system like this. It won't be consumed, you won't waste money, but it is more toxic, and so you don't want to get that in the atmosphere if you're leaking any kind of salt into the air, so that's important. Now, what we're going to do is I'm going to turn on the burner here. We're going to get this thing up temperature, and then I'm going to turn on the rest of the fans and the pumps, and we're going to see what kind of temperature we get out of this device. Now let's get this going. We don't need much heat. And then we'll turn on our pumps. It's going to get loud. Now we're flowing the desiccant. As you can see, the bubbles rising through there. Doesn't have to go fast. as the hot desiccant drives off the humidity with the counter current of air. And if we measure the velocity on the output here with the anemometer, we can determine what kind of actual volume we've got flowing here. So I'm going to hold this thing up here and see if you can see this upside down, and we'll get an idea of what kind of volume is coming through here. It's pretty good. 143, 129, 143. It's probably about 135 or so. So 1.35, which turns out to be about a 60th of a cubic meter, or about 20 grams of air flowing. So when we get the temperature differential across here, we'll multiply that by the number of grams of air and determine the actual wattage. So let's go ahead and turn on our pumps, get a temperature here. Okay, this T2 is the temperature of the air flowing out of this column. This may continue to drop for a little while because this water is effectively at room temperature, so it's going to take a little time for this to drop in terms of its equilibrium temperature, as we saw with the previous stack. Meanwhile, we'll look at the power that we're using. For the pumps, we're using about half an amp at 6 volts, so about 3 watts. For the fans here, we're using about 3/4 of an amp at 6 volts, so about 4 watts, so that's 7 watts. Over here for the pumps over there, we're using about half an amp at 6, so a total of about 10 watts. And over here, we're using about 24 watts. So we're using about 34, 35 watts in order to be able to cool off this air, which is really cold. It works really nicely. So if we figure that the room temperature here is 22 degrees centigrade, and we've got this temperature down here at about, say, 11 degrees centigrade, we have a drop of 11 degrees centigrade across this system. With 20 grams of air, that turns out to be about 220 watts of cooling with about 34 watts of input. So if you do the math on this, you figure that 34 into about, what, 220? You've got somewhere around 7, a cop of about 7, which is a little better than twice what we demonstrated with that air conditioner, including all the additional fans and the pumps. Now, one of the important things, though, is that the thermodynamic efficiency of this system is actually only about half that of that air conditioner over there. And the reason being is that we haven't included the heating stage in the process. This stage here will require about 3 times as much power as is being used by the electrical system here. And therefore, you'd get a cop of about half of what you get from that air conditioner. But before you say, well, then, what's the point? The point is that we don't need to use expensive heat to do this. If we burn, say, natural gas, we can produce the same number of joules of heat for about 10 to 20% of the cost of electricity. So running this kind of an air conditioner is still substantially more efficient, cost-wise, than running a typical air conditioning system. But you can go further. You don't even need to use a consumable. With the cost of 1 or 2 watts of pumping by one of these little solar heating pumps, you could run this up to a solar heating panel on, say, your roof and do the desiccation heating with free energy from solar. And when it's hot during the day, that's basically when you want the air conditioner to be working. And so therefore, that would allow you to keep that same 2-to-1 differential over a standard system. The German company that I talked about earlier is combining this kind of a system, actually, with a standard phase change air conditioner. And the elegance of that is that they're using the hot output from the air conditioner to drive the desiccation process. And so by doing that, what they can effectively do is they can remove the evaporative stage from this system. In humid environments, the majority of the energy that's extracted by an air conditioner is not to cool the air, but it's as a dehumidifier. That's what all those droplets are on the coils in a standard air conditioner. If you can effectively do the desiccation process with waste heat from your air conditioner, you can effectively allow the air conditioner to just cool the air, and they're obtaining efficiencies of about 2-to-1 as well. They are not using the evaporative pre-coolers that we are, so I have a suspicion that in that kind of a system, we could probably boost the efficiency even higher. In addition, This kind of a system right here has the cooling capacity that would be about half what we need for a room as large as this lab, but it is very easily scalable. This PVC tubing is available in 100 millimeter, 200 millimeter, even 300 millimeter diameters, and up to about the 200 millimeter size, which is 8 inch. These parts and pieces are still very inexpensive because this is mass-produced consumer grade material. And consequently, you could upgrade this substantially and improve the size and the capacity. But furthermore, the pumps that we're using, as low power as they only use about 1.5 watts. These pumps are about 20 times the capacity of what you need to simply dribble the liquids down these columns. And so no matter how big you build this, you really wouldn't have to add any additional pumping power. Furthermore, the fans that we're using here are far away from optimal. These axial fans are not designed to produce pressure. They're designed to move large volumes of air with no pressure. If we use a low-speed centrifugal fan, like the kind that you'd use for, say, a shop dust collector, you can increase the pumping efficiency against the resistance of these bioballs or whatever you're using about 2 to 2.5 times over what we're doing here. So with an efficient brushless motor, again, scaling this up would improve the efficiency even further. So the biggest expense that you might actually have in a much scaled system would actually be the bioballs. We've got about $30 worth of bioballs placed in here, and in a large system that could represent a fair investment. But there's another alternative. If you take used empty water bottles and you crush them up, put the lid back on, you effectively have a poor man's bioball. It's recycled trash. It doesn't fit very well in the top of something this small, but certainly in a larger scale, this would be a very cost-effective way to provide the surface area that you need for evaporation. There's about $120 billion a year spent on generating electricity, and it's estimated that about 10% of that, or about $12 billion a year, is used for air conditioning of buildings and of homes. And if you can double or even more than double the efficiency of air conditioners, you could save as much as $6 billion worldwide. And all we ask is that you subscribe. It wouldn't help if you link to the channel and link to the video. We'd really appreciate that. But I hope you found this interesting, and I want to thank you very much for watching. And you have a wonderful evening. Stay cool.